Okay, hi. This is Dr. Matthew J. Trom. This is the introductory lecture to heat transfer, which at UF has a course number of EML 4140. Um, Normally, when I start giving these recorded presentations, I just mention a few things, so hopefully I won't forget. So first is this lecture corresponds to a set of readings that have already been assigned. Ooh, let me get my laser pointer out so you can actually see what I'm pointing at. There we go. All right. So these readings have already been assigned in the course textbook. So section 1.1, 2, 3, 4, 5, and 6, it's basically all of chapter 1. So please read that in parallel with listening to the lectures. I'm hearing that some people like to read, some people like the slides, some people like kind of verbal description of what we're doing. So I'm going to try to accommodate all those different learning modalities to the extent that I can. Um, and if you are looking at this slide deck after this recording, there will be a link here. I don't have the recording done yet, obviously, because I'm making it right now, but there'll be a link right here. Um, that's the link to like the permanent location of the video on a University of Florida. I think it's a Zoom cloud, and there will be ADA compliant transcription, so you'll be able to read what I'm saying if you cannot hear what I'm saying. Okay, so this is the first module of the class. We're going to do a little bit of a course introduction, and then this module is an introduction really to conduction, which is the first of three heat transfer modes that we're going to study. Um, but because this is the introductory lecture, I'm going to just sort of touch on all three heat transfer modes, conduction, convection, radiation, and then we're going to kind of do a deep dive into conduction, and we'll forget about the other two for a bit, and then we'll revisit those later in the semester. So if you need to contact me, the best way, really, honestly, is Microsoft Teams. My email inbox is just so cluttered with junk these days that I can't actually find anything in there. So if you want to email me, here you go. But Teams is actually a better place. And if you want me to actually see your Teams message, please use the at symbol, like at Matt Trom, because I get a lot of Teams messages too, and only the ones that are added to me are the ones that I actually like can find and respond to. So okay. Um, if you've taken a class with me before, you know that I like to start with a meme or something that's representative. And boy, I feel like for this class, this is a very representative meme. The dumpster fire response team. So this class, as you will see, is not meant to be taught this way. It is not meant to be taught online, remotely, asynchronously. And so we've had to do an awful lot of kind of cobbling together different technologies very quickly to try to make the class work in an accelerated summer semester when everybody's off doing internships and co-ops and nobody is physically present. Weirdly, at University of Florida, there is no lab associated with heat transfer, which is very weird. That's like it's just almost unheard of. No other school I've ever taught at, I've taught at 7 in my life, has ever not had a heat transfer lab. So as you'll see, we're going to add a lab component as well, but the lab, of course, is going to be a take-home kit-based lab, um, which is causing its own challenges because some of you are not in the country this summer, which I didn't think about when I decided we were going to do a lab. So I appreciate everybody's kind of grace and patience with me and the teaching team as we work through all these problems and make sure that the class functions and all the technologies work and they all integrate together. We're still not totally there, but it's better than it was on Monday for sure. And I should also mention there was for those who don't know, there was a Canvas hack. So the entire like global Canvas system got hacked like literally 2 days, 3 days before classes started. And so I have also been having to play catch up inside of Canvas because I had the whole course all created and then it went poof. And then when Canvas came back on, everything that I did was gone. So I had to start over again from scratch, like literally after class started. So anyway, um, things will get better, things will settle. But for right now, the class probably feels a little bit like a dumpster fire. And yeah, I know, and I'm sorry. We'll we'll make it up to you. Um, Another, well, this is sort of a provocative slide to start with, but another thing that I want to say is, just to give you kind of a sense of my overall philosophy as I've been approaching this class. So, this is an article that came out of the New Yorker magazine a few days ago, May 12th, 2026, by J.C. King, and the title is Why the Future of College Could Look Like OnlyFans. And if you're not familiar with OnlyFans, it's kind of a racy website where like amateur people will basically you know I'll leave it to your imagination. Anyway, so this I think is a very provocative title for a very interesting article. But what Jay Kang is arguing here is basically that universities have become generic. Their education is commoditized. And let me move to the next slide, and I can show you why that's important to us. So universities have become basically commoditized in that a heat transfer class at University of Florida is equivalent to a heat transfer class, especially undergrad level heat transfer class at UC Berkeley, University of Michigan, Georgia Tech, Harvard, MIT, Stanford. It's all the same class, and they're effectively interchangeable. And that's a result, particularly for engineering, of our ABET accreditation process and having all of the programs that are accredited. And of course, you have to be accredited in order for your students to sit for the FE exam, the PE licensure exam, and become practicing professional engineers. It's often a prerequisite to get into graduate school, master's, and PhD programs in mechanical engineering, prerequisite for many, many, many jobs out in the professional world. So you cannot let your ABET accreditation lapse. And of course, the ABET accreditation has kind of forced us all into this commoditized, interchangeable kind of modality where heat transfer is the same class everywhere. Um, I think what you guys are discovering in the real world is that employers are seeking some differentiation, right? Everybody takes the exact same classes, and by and large, everybody gets relatively good grades. And so classes and grades are no longer signals of any sort of differentiation. And so employers are looking for, other things on a CV to basically make hiring decisions. And students have picked up on this, and you guys are increasingly relying upon extracurricular activities, clubs, Greek, fraternities, sororities, um, design competition teams, your own, personal passion projects. All that stuff is great. But you're relying on that for differentiation, right? And that takes more time, time away from your classes. But of course, you have to do well in your classes because everybody gets a relatively good grade in their classes these days. And if you don't, you're kind of a strange outlier. You lose access to um, doors that would otherwise be open to you. So you guys have an enormous demand on your time, and this is driving what the university is calling a mental health crisis among college students. But in short, it's the anxiety that you guys are feeling, having to like balance all this stuff. I think is becoming more and more palpable. So, and the faculty are aware of this, right? So, you guys are suffering because the world is the way it is, and we get that. So there's another element of this, right? It's like the perfect storm of bad. So without any sort of pedagogical innovation, which is sadly sometimes true at large public research universities like UF, where the focus is actually faculty doing research as opposed to excellent instruction. So sometimes faculty will just put a class on autopilot, and it's adequate, but it's not innovative. Um, in that kind of world, right, AI is going to replace all of us. So I say AI will plausibly replace what many faculty do if those faculty are not being innovative in their classes. Um, this is frightening, but it's also, I think, an opportunity, because AI has been trained on existing human knowledge, right? So AI, at least at the moment, cannot be creative, cannot be innovative. It can simulate creativity and innovation, but if you actually have a deep conversation with it, you'll discover that it's just regurgitating stuff that already exists. It cannot be creative. And to make matters worse, AI is programmed to be sycophantic, which means that it basically tells you you're awesome even if you're not. Um, and that is an intentional and now documented technique that's used by major AI companies to drive up engagement. And of course, the more engaged you are with your AI, the more tokens you're spending, and that's generating revenue for the company. So AI is sort of now become this, what I describe as a non-innovative yes man. And so you can actually see all these things tied together are making this problem of commoditized education worse and worse and worse. So what are we doing in this class that tries to break this pattern? So I want to provide value for you guys, and I want to do that in a way that provides experiences and engagement that AI cannot replicate. And so what I'm hoping to provide is what I'll call frontier expertise, right? So I'm an active researcher, both pedagogical researcher and in the energy thermal fluid sciences. And so I'm doing stuff that AI has never had a chance to, scrape or read or internalize because it's all brand new, right? A lot of it isn't even published. So some frontier expertise, some mentorship. You guys might have noticed that I've already asked for your resumes. I've asked you for your LinkedIn profiles. So your professional development, and making sure that you guys get placed in internships and jobs is a really important outcome for me, right? And an important outcome for this class. Um, we also want to make sure that you get some experiential learning, some hands-on learning. That's where the lab kits come in. Heat transfer should not be a theoretical class. It should be a class with laboratory experiments. So you guys are going to get some of that hands-on experience. And then, of course, access to professional networks, right? So I have a network now that I've been at University of Florida for 7 years, and my professional career goes back, 20, 21 years past that, and have a pretty substantial national, if not global, network. The last 7 years, I've been populating it with Gator engineering grads, mechanical and aerospace engineering grads. And you guys will now have access to that network. And I will work very hard to make sure that you guys get placed in internships and jobs as a result of knowing me and interacting with me and being in my network. Um, so let's go back to this idea of the OnlyFans comparison, which is that students are essentially paying for something differentiated when they enroll in a class, and if not, they're just going to get a canned kind of AI version of a class that's otherwise commoditized. So it's meant to be a metaphor. But it's, I think, an important way of thinking about what we're doing in 2026 in higher ed. So my goal is to make sure that you guys as students will benefit from direct access to me, right? Presumably, I'm a subject matter expert. At least, I've got the credentials that suggest I am. And the goal is to provide a personalized, mentor-driven, and reputation-based learning experience for you guys. So that's the overall philosophy. Let's look at a few interesting numbers and facts. So, the first one is this is a large land grant public university, one of the largest universities in the country, and our department is the largest department at one of the largest universities in the country. And our enrollment is going through the roof. It is increasing. I think it's fair to say, like geometrically, if not exponentially. I think I heard the new incoming freshman class is 950 students. So there are a lot of you, and I have up until I got my job at UF. Um, Always taught it at small, both public and private, but small programs. Programs where enrollments were quite a bit lower than they are now. The challenge that I have on a daily basis is how to provide you guys with what I would describe as a private school level of interaction and access when there's 165 of you enrolled in the class. So you guys will see, right? We use Microsoft Teams. I try to be as responsive as I can to as many of the questions that come in as I can be. Try to be accessible. I'm up. You guys will know this. If you've taken fluids with me, I'm up until sometimes 2 or 3 in the morning. Answering questions because I find that most students are nocturnal like me. So I try to operate on your schedule. Um, but there are 165 of you, and this was an intentional choice on my part. The department originally wanted to cap the class at 80 students, and I'm aware they changed the prerequisite requirements for EML 4501, the first class in the capstone senior design sequence for mechanical engineers, and required heat transfer as a prerequisite for that class. So I think this enormous enrollment is in response to you guys realizing that you need heat transfer in order to get into that class in the fall. And perhaps the advising office either wasn't aware or were sort of caught unawares that that requirement was changing. And so in a way, I think this class is an anomaly. I think this 165 students is kind of an emergency reaction to changing requirements. Like I said, the department originally capped the class at 80, and I said, nope, just open the floodgates and let everybody in who needs the class. We will give them a good experience, but I don't want to leave anybody out. So um, anyway, hard to provide an individualized kind of private school experience when the class is so large, but I'm going to do my best, or I'm going to die trying. Another thing is that this class is 100% online, asynchronous, and remote. So when Professor Griffiths, who is our associate chair of academics, said, "Oh, hey, Matt Trom, you want to teach heat transfer?" I'm like, "Bro, I want to teach heat transfer. I love heat transfer." I've taught it a bunch of times at other places. I've never been able to teach at UF. I've always asked them if I could, and this is my chance. So I'm really excited to do this. And then he's like, "Great, I put your name." So this is Griffiths, right? "Great, I put your name on the roster to teach it. Oh, by the way, the class is 100% online, asynchronous, or remote. Have a nice day," right? I'm like, "Oh my God, what are you talking about?" So this class, heat transfer, has never been taught in this modality at the University of Florida ever. In the university's nominally 150-year history, the department's 120-year history, we have never taught the class this way. So I am figuring out as I go how to teach heat transfer online, asynchronously, and remotely. So I appreciate your patience as I try to figure that out. Another thing that I'm a little cranky about is the university this summer mandated the use of simple syllabus, which I think in the long run is going to be great because syllabi will finally be kind of uniform and simplified and easier for faculty to create. At the moment, simple syllabus is the word that I would describe it as a dumpster fire on a train wreck in an airplane crash. It was not ready, in my opinion, to roll out. They did it anyway. And you guys, I think, have seen the result. The syllabus that I've been able to put together in this class has got like a ton of mistakes in it. It's missing a bunch of information, and there's no way for me to change it. It's all locked in that way. So I apologize for that. I am embarrassed on behalf of the university that they rolled out this platform before it was ready, but here we are. And I have actually inquired if I could just give you guys a syllabus of Microsoft Word the way that I always used to do it, so that I can put what I want on there and it's formatted correctly and it has all the correct information. And I was told by several people, several layers above me in the hierarchy, that I'm not allowed to do that, that I must only give you a syllabus on simple syllabus. So we are going to roll with it. It is going to be okay. But the syllabus that you guys have is a lot less detailed and a lot more riddled with errors than I am comfortable with. So sorry, but that's what the university has prescribed for us. Okay, so let's talk about some of the better things. So We are going to use the platform Perusal for asynchronous group discussions. I thought a lot before this class started about how I wanted to, interact and engage with you guys, given that we're asynchronous. And I think Perusal is a great platform for that. This is the first time that I've used it in a like four credit large enrollment type environment, right? I've used it for other things where it was, kind of like extra credit type stuff or, not for credit type stuff. But so I am like you guys working my way up the learning curve with this platform. But what I did not want was to just give you guys, my boring talking head for, 3 hours or 4 hours or whatever it is of lecture per week without any way of interacting with me. And interacting with each other like you would be able to do in a normal lecture class. So we're going to use Perusal. We'll see how that goes. Um, but to provide that interactivity that you guys aren't going to get in a asynchronous environment otherwise. We are also going to pioneer the use of Lecture Hat. So Lecture Hat is an AI-enabled homework assistant. It was created. It's a startup company out of University of Florida. Um, this is the first class it has ever been used in. So we are going to pilot that for the creators of this software platform, and we're going to give them some feedback on how well it works. So the goal here ultimately is we're going to do a couple homework assignments without Lecture Hat to get you acclimated, and then we're going to add Lecture Hat in and give you a couple more homework assignments, and then you're going to give the developers some feedback about how helpful or not helpful it was. But that's experimental. And then finally, as I mentioned before, we are going to use hands-on lab kits because heat transfer should be a lab class. And the fact that it's not at UF is kind of frightening. So it is now. Um, I tried really hard to find a pre-existing lab kit because that would be way easier to just find something that already exists on the market, have you guys buy it, and then we're good to go. Turns out doesn't exist. Heat transfer has existed for 300 years, and nobody has ever thought to create a small, portable, mailable kit, educational kit to teach students how to do heat transfer. So, in addition to a lecture hat being, first time it's ever been used, this is also the first time that a heat transfer lab kit has ever been used, and that's not just at University of Florida. This is the whole world. Maybe somebody did something like this during COVID, but nobody has documented it, and there is no existing commercial product that came out of that experience. So we are working with Beyond the Benchmark Engineering. You probably remember them if you took ENG, I think it's 1006, the Intro to Engineering class. They made the little alligator robot kit. You probably saw that when you were a freshman if you took that class. So I worked with them like all spring to come up with this kit. They manufactured 170 of them in like 2 weeks. And that's what we're doing. So, in terms of differentiation, this class does not look like any other heat transfer class that exists anywhere else in the world, right? So if you go back to, uh, you know, college looking like an OnlyFans experience, um, where or sorry, college being let me say commoditized, right, where everything is the same, and students looking for kind of a metaphorical OnlyFans experience where there's some differentiation, right? Because you guys need differentiation to go out and be competitive for jobs. This class is where that is going to happen. You guys are going to be able to tell stories to potential employers, to graduate schools about your heat transfer class that nobody else in the country is going to be able to tell. It's going to be incredible. So, we're dealing with some challenges right now, but I think in the end, this will all work out and make this class both, a great learning experience for you guys and also substantially differentiated from any other heat transfer class being offered anywhere else in the world. So this is the lab kit. Um, we threw this together over the span of about 15 weeks in the spring semester. We'll have more details about this when you guys receive it. My understanding is that the UF bookstore has now bundled Perusal with Wiley Plus, which is the publisher for our textbook. which is Heat and Mass Transfer by Bergman and Levine. I think it's eighth edition, and the lab kit. So those are all bundled together. I was able to negotiate with the bookstore to get all access pricing. So I realized that all these things are a little expensive, and I apologize for that. But it's actually a lot less expensive than it would have been if we had you guys get all three of these things separately. I think the original price they quoted me was close to $400, and we've knocked it down to below 200. I think it's 184 now. So this is the kit. It has all the stuff we need to do conduction, convection, radiation experiments. It's got a data logger. It's got a infrared thermometer. Um, it's got an ice cube tray. You could make a drink while you're at it. Well, we'll dig into this more as the semester goes on, but this is the first time a laboratory kit has ever been used in a heat transfer class in a documented way anywhere that I could find in the literature. So very cool. All right. So if you'll indulge me for a moment, I have to tell a war story, right? So we are always recommended by UF Center for Teaching Excellence to start classes by, talking about ourselves a little bit. So look at how young and how thin and how attractive I used to be. This was 19. No, 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 not 19. No, I'm not that old. This is 2007, 2008, something like that. So 18 years ago. Um, anyway, I was a young assistant professor working at a university in Texas. And we were approached by a company that needed some help commercializing their solar-fired organic Rankine cycle. The company was called Solar Logic. Greg Bull, standing here next to me, he was the CEO of the company. And this was very cool technology. I wish I could spend more time talking about it, but basically, these guys are using solar power to drive a Rankine cycle. And if you're remembering back to thermo, Rankine cycles were the big ones, right? The ones where there's a phase change from liquid to vapor. And lots of benefits associated with that, but also very hard to make those small. And these guys were trying to miniaturize this thing to the point where it could actually fit on a trailer and be moved from one place to another for military power generation, remote power generation applications, and also for commercial applications. They wanted to install it on a roof, a lot like we do with normal solar panels today. So. This is what they ultimately built, right? So they had, and I've got it color coded so that you can see what's what between the schematic and the real thing. So just like any other Rankine cycle that you've seen in any of your thermo classes, we had a pump which pumped. In this case, it was water, but eventually they went from water to, I said organic, right? So it was an organic fluid. Not water, but one of the coolants that they commonly use to cool electronics was the working fluid of this thing eventually. But they pumped it in the liquid phase into the boiler. It absorbed energy from these parabolic troughs, right? There's this little concentrator in the middle collecting sunlight. The fluid boiled, vaporized. It got run through a turbine. And then at the end, you guys remember from your Rankine cycle experience, you have to reject the entropy somehow, right? So they ran the now depleted working fluid through a condenser, recondensed it back to a liquid, and the cycle continues, right? So you can see here, here's the turbine, which by the way was a Tesla turbine. This is a big area of research for me, bladeless turbines. Here's the condenser, here's the pump. And then this thing was connected to these outside solar concentrators. That was the boiler, right? So those are the components. Um, so in the boilers, they had these heat collection elements, HCEs, right? What's an HCE? Well, it is a tube that has a glass outer housing. It has then an inner tube, which is made out of metal. I think these were copper. They have a anti-reflective coating, which gives it this. You can actually see one here, right? This anti-reflective coating that makes it look almost black. Um, and it ran the working fluid through it, right? First water, and then later an organic working fluid. And then there was a vacuum in between, right? And the purpose of the vacuum was um, the sunlight enters through the transparent glass. It strikes this highly absorbing, very anti-reflective surface. It heats up the metal. The metal heats up the water. You guys have all, in theory, taken fluids, and so you could actually calculate, right, all of the flow associated with like flow through a pipe, pressure loss, and what the velocity profile and stuff looks like in here. That also is important to heat transfer. We'll get to that in convection eventually. But it would heat up the working fluid, and the working fluid would then go out to the turbine, and all that energy would get extracted as useful mechanical work. But you do not, once you've heated up the water, want to let any of the heat out, right? So you want to evacuate this space, put a vacuum in between your inner tube and your outside glass. And that vacuum, I say vacuum, question mark, that vacuum provides substantial insulation, right? Preventing heat transfer out, so that you've got all that heat absorbed so you can run it through the turbine and get mechanical power out of it. So Solar Logic, in an attempt to try to save money, which companies do, right? They want to make money by saving money. They outsourced the manufacture of these heat collection elements to a manufacturer in Asia, and the heat collection elements were coming back. And they were not functioning correctly. They were not functioning nearly as well as the company had anticipated. And they were asking the question, well, is there actually a vacuum in this space? Did the manufacturer evacuate the space, or is there air in here, right? And if there's air, there's the possibility for even convective heat transfer, right? The motion of air transmitting the heat. And there's definitely the possibility of conductive heat transfer through the gas layer from the surface to the glass, and then conduction through the glass to the outside. So they were trying to figure out if there's vacuum in these spaces, as was required in the manufacturing contract, but they were sealed, right? So there's no way, without actually breaking the glass, to determine whether there's vacuum in here. So we had to come up with a technique. There was a non-destructive technique to figure out whether these heat collection elements were evacuated or not. So here's what we came up with. So we basically developed a heat resistance model, which we will talk about when we start talking about conduction. So we identified all of the different resistances to heat transfer. You can see some of them run in parallel, some of them are serial, but associated with all of the different surfaces and all the different components. And we figured out what that, in an ideal situation with a perfect vacuum in here, what that should be. It should be something about 0.66 Kelvin per watt. And then we said, okay, now that we know what this resistance model looks like, and we have a sense of what this heat transfer resistance should be, we can actually pour liquid water at a known temperature, right? So we boiled the water, and then we poured it into the heat collection element. And you can see here, there are these kind of wires running out. Those were all measuring internal temperatures inside this evacuated heat collection element. And from those temperatures, we were able to develop this cool down curve, right? So the water goes into the tube. The tube just sits out on a lab bench, and over time, heat transfer from the inside of the tube through this combination of resistors it allows heat to basically leave the system. And as heat's leaving the system, we were recording the temperature as a function of time. And so we were able to come up with this experimental curve, right? So you could see the black curve there, right? Not too bad, because our model was this gray curve, right? Pretty darn close. So feeling pretty good. I will mention that even though we calculated like the ideal resistance for these HCEs to be 0.66, we found experimentally through a number of trials that the correct number is actually 2.22, and that was because we made a number of simplifying assumptions. But we were able to get a pretty reliable experimental value of 2.22 kelvins per watt for a totally evacuated HCE. And this, by the way, is the equation that we used. And we're trying to do something called minimize the SEE, minimize the standard error of the estimate. But as you can see, by combining this theoretical model with some experimental values, we're able to get really good agreement between the model and the experiment. Right. So we've got time on the x-axis, we've got temperature on the y-axis, and you can see this thing cooling down over time as it's losing heat through this equivalent resistance. So this was kind of amazing because now we have a technique to figure out what this resistance is, thermal resistance, without actually having to like break open the tube to figure out whether there's vacuum in there or not. And the thing that was most important is R3. Where's R3? Here's R3. 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 This is the resistance associated with the evacuated annulus, right? So that should be, there should be no conduction, there should be no convection in there. That should just be a radiation heat transfer. But if this resistance is subject to conduction or convection, if there's gas in here, this resistance is going to be a lot lower, and you're going to end up with a lower overall resistance to heat transfer and a faster cool down. So we were able to compare a tube that we knew was evacuated because it was manufactured in the US by Solar Logic to all the tubes that were coming in from the manufacturers. And the takeaway is that Solar Logic implemented this non-destructive thermal testing technique on all of the HCEs that got shipped from their overseas manufacturer. And the company found that many of the units' heat transfer resistance was lower and outside the experimental uncertainty compared to the known evacuated collectors that we tested that were manufactured in the US. So what that means, lower heat transfer resistance, that means that there is more transfer of heat through the system than should be there. And the end result is that we were able to, without any destructive testing, completely non-destructively, we were able to figure out that the manufacturer was not properly evacuating their HCEs. So Solar Logic had to go back to the manufacturer and get them to improve their process. And they eventually did, and it worked out fine. But the manufacturer, they actually had no idea that their process was not working correctly to pull a vacuum on the inside of these HCEs. We were able to figure it out completely thermally without any destructive testing. So this was a bunch of undergrad students that I worked with in my research lab in Wisconsin to do this. We ended up generating a paper out of it. So here's the paper. These guys are all undergrads. There's me, right? Final author on the paper. Experimental measurement of a heat collection element, thermal resistance for concentrating parabolic solar troughs. And this showed up in the proceedings of the International Energy Conversion Engineering Conference in, about what is this? About 12 years ago. Here's the front page of the paper, right? So you guys can look this up and read it if you want to. But this is now a just accepted technique that's been peer reviewed and accepted out in the literature. So just I think a very, very cool example of an application of heat transfer, in this case to a new energy conversion technology, concentrated solar power with a coupled organic Rankine cycle for small scale power generation, small scale remote power generation. And just a very cool example of using knowledge of heat transfer, right? Like knowledge of this cool down curve and the knowledge of this thermal circuit to be able to evaluate the effectiveness of this technology, or I should say the manufacturing technique underpinning this technology without actually having to do any destructive testing. So just a cool story. Okay. Let's get into some content now that I've told you a little bit about my life philosophy and some heat transfer work that I've done that I just thought was very cool. So, what is heat transfer? Heat transfer is a temperature gradient induced thermal energy transit. Very simple. It's anytime you have two different temperatures anywhere in the universe, there's going to be heat transfer between those two different temperatures. I use this term thermal energy. You guys, I hope, have seen that term already in your thermodynamics class, but just as a reminder, thermal energy is the manifestation of combined translation, rotation, vibration, and electronic states of atoms and molecules that comprise matter, right? So if you think back to like your thermo class, this is like the wobbling of the atoms in your lattice that we see as temperature, right? So it appears on a macroscopic scale as a temperature. So I say that here actually, a macroscopic manifestation of the atomic scale activities linked to the temperature of matter. And for our purposes in this class, there are going to be three different types of heat transfer. There's going to be conduction. Where is it? There it is. Conduction, convection, radiation. I really like this image because it shows all three simultaneously, which is what happens in the real world, right? We're going to sort of silo them out and talk about them individually, but in the real world, all three happen at the same time. There are, I should, just mention for completeness, there are other modes of heat transfer other than these three. They are usually very, very small compared to these three modes of heat transfer. And a lot of times they only occur in very, very kind of weird specialized situations, like when something is really, really small, like on the nanometer scale, or if you have a situation where you've got gas, but it's like incredibly rarefied and you're in like Knudsen flow, you can get heat transfer that's kind of carried by individual molecules. But for our purposes in this class, most engineering applications only have to worry about conduction, convection, radiation. So let's dig into those a little bit more. So three primary modes of heat transfer. Conduction is heat transfer through a solid, typically or sometimes a fluid, but the fluid has to be stationary. So it's a very specialized case where the fluid is not moving. You can get conduction through a fluid. Convection is the combination of conduction and motion of the fluid. So that's the case where you have like flow over a flat plate, flow through a channel, even natural convection. So like buoyancy driven flow. We talked about all three of those in my fluids class, and hopefully you did too if you didn't take fluids with me. But this, by the way, is why fluids is the prerequisite for heat transfers, because to do convection, you have to know what the flow field looks like. And to know what the flow field looks like, you have to have taken the fluids class. So convection, basically heat transfer due to moving fluid. And then there's radiation, which is an energy transfer between surfaces at different temperatures caused by electromagnetic waves, right? So basically photons. And we'll talk a little bit about that, and then we're going to put it aside for a while, and then we'll come back to it at the end of the semester. But radiation is very cool because everything is radiating to everything else, and so it's a little complicated, but also tractable and very interesting. So I say here, conduction and convection heat transfer require temperature variations in a material medium, right? So you have to have a solid or a liquid to conduct heat. That's because you've got the individual molecules or atoms in a lattice, and the lattice is vibrating, and those vibrations get transferred from one layer to another in your lattice. And that transfer of vibrational energy is a transfer of heat through conduction through whatever your solid or your liquid is, or your fluid is. And then convection, right? You have to have some sort of gas, some sort of liquid fluid of some kind that's moving in order to provide like bulk motion of fluid. Radiation is different. Radiation heat transfer does not require a material medium. It is energy transfer through photons, through electromagnetic waves. And so you will find, at least for terrestrial applications, most of the time they're dominated by conduction and convection, and radiation is very small, often just neglected because it's so small. And then when you get into like space applications where there is no, matter floating around you, all of a sudden everything becomes radiation dominated, and there's very little conduction and convection. So um, different modes for different environments. Okay. Another thing that I want to mention right off the bat, you hopefully will remember this from thermo, but this technique is used an awful lot, and so I wanted to mention it right up front. It's called surface energy balance. So heat transfer, as I've said a couple times now, is almost always multimodal. There's almost always conduction, convection, radiation all together. In this class, we're going to break them up and look at them individually. But in the real world, you do have to deal with all three of them simultaneously. And there are a number of problems in the book where they are dealt with simultaneously. So I want to make sure that you guys can get some traction on how to do that. So a good way to kind of deal with these multimodal heat transfer problems is to place a control volume, right? So remember, control volumes from thermo and fluids. To place a control volume at the surface where simultaneous heat transfer processes are occurring. And this is a special kind of control volume because it's a control volume that has no mass in it, right? It's shown here basically is drawn with control surfaces on just, the very inside of a surface where multimodal heat transfer is occurring, and then another control surface on the very outside of where that is occurring. But this thickness is greatly exaggerated, right? This is meant to be basically, approaching zero thickness. So you've got this very, very thin, very, very thin control volume, and it's so thin that it does not contain any mass, but it does account for all of the fluxes, the inputs and outputs of thermal and, to be fair, also mechanical energy, thermodynamic energy um, through it. And so once we've got this control volume, then we're going to perform an energy balance, just like you've done in thermo thousands of times. In a steady state situation, the change in energy with respect to time is zero. For the system, right? Which of course is also true if the system has no mass because it can't store any energy. And so all of the energy flux into your control volume minus all of the energy flux out of your control volume has to equal zero. There's no opportunity for storage. And we know, at least for this class, that there's only three kinds of heat transfer. And so this expression from the first law of thermodynamics basically just becomes an expression of conduction plus or minus convection plus or minus radiation in this control volume is equal to zero. And I should mention two things. So one, plus or minus, because if the energy is going into the control volume, it's positive, right? And if it's leaving the control volume, it's negative. So I leave these as plus or minus so that you can choose the appropriate sign for the direction that the heat is moving. And then I'll introduce this notation of kind of this double prime. I'm, by the way, following the notation of the book, right? So the book uses lowercase q as a heat flux. And then, when I say flux, I mean like heat transfer rate, like energy per time. And then this double prime is per unit area. So single prime is per unit length, double prime per unit area. No little quotation marks there, no double hash marks is just a pure value, not on a per length or per area basis. Okay, so we add all those up, they equal zero. And then we haven't seen these equations yet, but we will in a moment. There is a kind of standard conduction equation, which is this. There's a standard convection equation, which is this. And then there's a standard radiation equation, which is this. And you just plug in those standard equations into this energy balance. It's still equal to zero. And now you could start seeing how you could solve for temperatures, right? Because that's usually what we care about in the world of heat transfer is how hot things are getting in terms of their temperature. And so the ultimate goal most often is to be able to solve for temperatures. And so you can sort of see the progression from first law of thermodynamics to three modes of heat transfer to an equation that has temperatures in it that you can solve for. So, okay, we'll practice this in a little bit because I've got an example that does this. Okay, right. So let's start with conduction, the first of our three heat transfer modes. I'll just very quickly mention this equation, which is the conductive heat flux equation, is often called Fourier's law of conduction after Jean-Baptiste Joseph Fourier lived from 1768 to 1830. Here's his picture from Wikipedia. So this equation is simply that the heat flux, which again is energy per time, right? So power per unit area, that's what this double hash mark represents, is equal to minus K, which is thermal conductivity, multiplied by the temperature gradient. So this is a spatial change in temperature with respect to distance, respect to location. We live in a three-dimensional world, so all three spatial directions. That's what this upside down triangle del represents, right? We're basically taking a derivative of temperature in all three spatial directions, X, Y, Z. For our purposes, at least in the beginning, we're going to start with a one-dimensional simplification, and then we'll add the complexity of multiple dimensions later. But this is the basic equation. Um, this negative sign often trips people up, myself included. This negative sign is there because heat always moves, if you remember from second law of thermodynamics, always moves from hot to cold. And so a lot of times you'll write this as like, it's actually here, right? T2 minus T1, T2 minus T1. And T2 is colder than T1. And so you end up with a negative temperature difference here, and this negative sign then negates the negative temperature difference. It gives you a positive heat flux. So that's where this negative sign comes from. It's by convention put in there to negate the negative temperature that comes from the temperature gradient. Notice the units, right? So we've got watts per meter squared. For thermal conductivity, we've got watts per meter Kelvin. And then for temperature gradient, we've got Kelvin per meter. And when I multiply these two things together, I get this, right? So Kelvin drops out. So I'm left with just watts per meter squared. Okay, so as just described, simplest case is one-dimensional steady-state conduction across a plane wall of area A and thickness L. We'll just leave those things as variables for now. We'll be able to plug in numbers later when we know specific geometries. And a constant thermal conductivity K. K is a material property. You can look it up. I will mention that it does change with temperature. So that's an added complication because you have a temperature gradient inside your object. And oh man, K is changing as the temperature is changing. And so this value might be different from one place to another. For our purposes right now, just as an introduction to keep things simple, we are going to just assume that thermal conductivity is a constant all the way through at some agreed upon set temperature that's relevant to the problem, right? So just like you guys did with thermo, right? Assuming things like constant specific heats when you knew they were actually changing for an ideal gas. We're going to make this assumption just to simplify things to make these problems tractable, and then later on we'll relax that assumption once you get a little more experience. Okay, so I'm going to take my Fourier's law of conduction. I'm going to make it one dimensional, which means that I'm only worried about the heat flux in the x direction. My K is a constant, at least for now, so it stays. And then this delta T, or sorry, I should say delta T, temperature gradient is now just the change in temperature in the x direction, right? Because I'm one dimensional. And you hopefully remember from calculus long ago that a derivative can be represented as just a ratio of differences, right? Especially if something is linear. Dt dx is approximately T2 minus T1. These are temperatures of the surfaces, right? So here's T1, the higher temperature, and then here's T2, the lower temperature across this slab. This is the temperature profile inside the slab, Tx, and then this is the x direction, right, from left to right. And then the dx, well, that's just the thickness of the slab, right? So in this case, it's just L, thickness of the slab. And so that is my simplified Fourier's law of conduction for this kind of preliminary representative geometry. Notice it's still in units of watts per meter squared. If I want to put it in units of watts to get an actual heat, right? So thermal energy, I can multiply by area, right? So if the area of this slab is, I'm going to make up a number, 1 meter, right? I multiply this heat flux by 1 meter, and then I get the just the rate of heat transfer. So here I am doing that, right? Just taking this equation, multiplying by A to get the area. Oh, and by the way, just swapping T1 and T2 with this negative sign to make sure that everything stays positive and there's no confusion about where the negative sign goes. Okay, so that's conduction in a nutshell. Let's do a quick example. So we have I think it's a plane of glass. Yeah, glass plane. We're given the inner and outer surface temperatures. We're told that the plane of glass is 1 meter by 3 meters, 5 millimeters thick. And those temperatures are 15 Celsius and 5 Celsius. We're also given the thermal resistance of the glass window due to conduction. We're told that it is 1.19 times 10 to the minus third kelvins per watt. And we're told to assume steady state temperature. So let me just, since this is our first problem, let me just kind of break this down a little more for you. First thing, um, Celsius bad. Fahrenheit worse, but Celsius bad. Um, we are just going to take, as we'll see here, right, a difference between two temperatures. So you can use Celsius if you want to, because you're just taking a difference between two temperatures. But my God, please don't do that. Please don't do that. Please convert all of your temperatures into absolute temperatures, even if you don't need to. This is just a very, very good habit to get into. So you'll see I do it down here. I just convert 15 Celsius to 288 Kelvin, and I convert 5 Celsius to 278 Kelvin. And oh my God, that's going to save me so much trouble in the future. So please just, if you see Celsius, just convert to Kelvin. That should be like instantaneous. The other thing is we have not talked about the difference between thermal resistance and thermal conductivity. They're just sort of inverses of each other, right? So way back when I was talking about um, my war story about solar logic, I introduced a series of thermal resistances, and we'll see actually in this problem that thermal resistance and thermal conductance are just inverse of each other basically. So that's what this thing is. It's just a conductance, but flipped over. Um, okay, so we're asked to find what's the thermal conductivity of the glass in watts per meter Kelvin, and then we're asked what is the rate of heat loss through this window, right, with the same area. Yep. Okay. Cool. Um, all right. This is a drawing. I am really bad at drawing, so I borrowed this from the book, but you can see the geometry, right? So we have this square pane of glass. It's 5 millimeters thick, 0.005 meters thick. On one side, it's 5 Celsius, 278 Kelvin. On the other side, it's 15 Celsius, 288 Kelvin. We're told the area is 3 square meters, and we're given the conductivity. And we're asked to find, thermal resistance, not conductivity. We're asked to find the conductivity, and then we're asked to find the rate of heat transfer through this guy. Okay, let's do that. So thermal conductivity, as I mentioned, is just like the inverse of the thermal resistance. We're going to end up using thermal resistance probably a lot more than conductance, because you guys know from your circuits class how to combine resistances together to make more complicated resistances, resistors in series, resistors in parallel, to make equivalent resistors. So resistance is often used. So the thermal resistance for conductivity is just the thickness of the object divided by K divided by A, where K is the thermal conductivity and A is the cross-sectional area, right? So like I said, resistance and conductance are just like inverses of each other. They're basically interchangeable. It's just, it's one over the other one. Okay, so we know all these things, right? We know the thickness, we know the thermal resistance that was given, and we know the cross-sectional area of this glass plane is 3 meters squared, so we can plug those values in, and I got 1.4 watts per meter Kelvin is my answer. Green check. Hopefully you did too. Okay. Second problem is what is the rate of heat loss through by 1 meter by 3 meter window? So I'm going to just go to my conduction equation, right? So here it is in all of its glory. And I know everything. I now know, or I know the area, I know the conductivity, I know the temperature difference, and I know L. So I'm just going to plug all those things in. Here's me doing it. And out pops 8.4 kilowatts, 8,400 watts is my answer there. Green check. Got that one too. Hopefully you did as well. Okay. So that's conduction. Let's move on to the second heat transfer mode, which is radiation. No, dear God. Sorry, I've got radiation on the brain. Convection. There we go. Convection. So here's this is why, by the way, you had to take fluids as a prerequisite to heat transfer, because you have to know how fluids flow in order to be able to calculate heat transfer convection coefficients. So you might remember this one, right, from if you took my class. I love flow over flat plate. This is a prerequisite to airfoil design for fixed wing aircraft. I'm an airplane guy. So flow over flat plate is like near and dear to my heart. If you guys remember the final exam, right, we had a question about boundary layer development and the Blasius solution on the fluids final. So here's the velocity profile for flow over flat plate. Turns out, interestingly, there is also a temperature distribution profile that goes in the opposite direction of the velocity profile. So if you have a hot plate and you have cold air blowing over it, the temperature of the air right near the plate is going to be close to the plate temperature, and then it's going to cool down as you get farther up into the free stream. And there is actually a thermal boundary layer, which is analogous to the velocity boundary layer for flow over flat plate. But let me. Sorry, I'm getting way too into the. I love this stuff, so I'm getting like way too deep into the woods right now for an introduction. Okay, you guys know this guy, right? Sir Isaac Newton lived from 1643 to 1727. Newton did a whole bunch of stuff in physics, a whole bunch of stuff in astronomy. Probably a little less well known, but he also did a bunch of work in heat transfer and ended up having this convective law named after him, Newton's law of cooling. So here it is, just like with conduction. We're going to have some sort of heat flux in units of watts per meter squared, right? So energy per unit time per unit area. Um, it's going to equal to a or be equal to a temperature difference. So TS is the temperature of the surface from which heat is being transferred, and T infinity is the temperature of the surrounding environment or the surrounding air, right? Like far away from the plate, far away from the surface. Um, and then that temperature difference gets multiplied by H, which is the convection coefficient. This is like where the magic happens. So calculating these H values is actually very hard. And you guys will be expert at this by the time we're done. But for now, we're just going to give you these values, and you'll be able to calculate, convection problems with given H values. And then when we get a little bit more sophisticated, we'll show you how to calculate H, and that will work into your skill set. I will mention a pretty important pitfall here. The book does this and doesn't even explain it. I was like, what the hell is going on? TS and T infinity can swap places if needed, depending on which one of them is hot and which one of them is cold, right? So H is always a positive value. Your heat flux, you always want that to be positive in the direction the heat is moving. And so you might end up in a situation where the surface is colder than the ambient environment and heat is going from the environment into the plate because the environment is hot and the plate is cold, in which case these two can be switched. Right. So just, be aware that sometimes you're going to see this as TS minus T infinity, and sometimes you're going to see it as T infinity minus TS. And the book is doing that to get the heat flux to go in the correct direction. So just be aware. Okay. This chart is like a lifesaver. So yeah, by now you guys are, in at least the end of your junior year, probably into your senior year, fourth year, maybe even fifth year at UF in an engineering program. And I hope that you are familiar with the idea of like sanity checks, right? So you do a calculation and it's like, is this right? Probably not. How do you know whether it's right or not? So the book actually gives you a table for typical convection heat transfer coefficient values. There are multiple different kinds of convective heat transfer. We'll talk about them later. But there's essentially free convection, which is like natural convection, like buoyancy driven flow. And then there's forced convection, which is you have a fan or a blower or something forcing your fluid over your surface. And then those can happen for gases, liquids, and then you can also have phase change, right? So boiling and condensation. And these are kind of typical values for those different modes of heat transfer. So remember that this is here and in the book, because when we get to the point where we're calculating these H values, it's always very good to go back to this table and just to confirm for yourself that the value that you get falls within these numbers. I can't tell you the number of times I teach the capstone class, and I have the capstone students do heat transfer calculations to figure out whether their electronics are going to burn up. And a lot of times it's just free convection they're using, right? So just like natural convection to cool electronics. And they miscalculate H and they're getting values of like 500, like 1,000 watts per meter squared Kelvin for gas, right? For air. And I'm like, guys, that can't be right. And they're like, oh no, it's right. I did the calculation. I'm like, bro, it's not right. And it's because I have these numbers in my mind because I've used this chart so many times. And the students invariably will go back and they'll realize, oh yeah, I made a miscalculation here, but it's because they had this sanity check. So just remember this chart is here. This is very helpful. Um, and of course, as mentioned, there are multiple different types of convective heat transfer. So here's forced, where I have a fan that's blowing air over hot components. It looks like these are hot components of a circuit board. I have natural convection where I'm relying just on the buoyancy driven flow as a result of the density reduction of air as it gets hot to just move air naturally up through my heated components. And then I have boiling. I love boiling. I can't tell you, boiling heat transfer is so incredible. Where you're actually doing a phase change process at the heated surface, and that phase change is absorbing heat through latent heat of vaporization. And then you have these vapor bubbles that move through the liquid to the surface and release the heat from the top. Like, oh my God, so cool. And then condensation, right, which is also very cool, but it's the opposite of boiling convection. And this happens a lot in Florida because we live in a environment that's almost always 100% humid outside, 100% relative humidity. But so anytime you have like a can of soda or anything that's cold, water droplets will condense onto it. And in so doing, they will give up their latent heat of vaporization and heat the water on the inside, right? And then they'll drip off as liquid water droplets. So both of those are phase change types of convection. We'll talk about all four of these later on, but let's do an example. And I love this example. So I had to dig through the book to find this. This was one of the things I was going to give you guys for homework, and then I'm like, no, 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 I want this one for me. This one's too cool. As you guys know, I'm an experimentalist, right? And I love metrology. I love like different ways of measuring things. So this is really, really cool. Okay, so we have an experiment that determines the airflow convection coefficient. So we're basically trying to figure out how to calculate these H values in Newton's law of cooling with this apparatus. So airflow convection currents over a surface of thick stainless steel casting. And we do that by inserting thermocouples into the casting at known distances from the surface. And those distances are, at least in this case, so here's the surface, right? And we've got hot air at 100 Celsius blowing over this surface. And so we have a convective heat transfer coefficient, or convective heat transfer, I should say, convective heat transfer going into the surface. And what we are looking for is this H value, this unknown value for H, which is the convective heat transfer coefficient. These thermocouples, as I was about to say, are drilled 15 millimeters and 30 millimeters away from this surface, which is experiencing convective heat transfer. And it is important that they are normal to the surface, right? So they are along a straight line, which allows us to basically get away with one-dimensional conduction and recognize that these guys all just live on a linear temperature gradient. And we're going to use that to our advantage to figure out this H value. Okay, so we know from materials testing that this particular alloy of steel has a thermal conductivity of 15 watts per meter Kelvin, so that value is known. And the thermocouples, when this experiment is run, they measure a temperature of 333 Kelvin and 323 Kelvin. I converted them from Celsius to Kelvin for you. You're welcome. In the steel, when the surface is at 100 Celsius, which is 373 Kelvin. Okay, so interestingly, this is a problem from the book. They don't even tell you which one of these is like, 333 and which one is 323. I guess they do here. They call it T1 and T2. But you should be able to figure this out even without knowing, because what direction is the heat going, right? It's going from right to left. And so it's going to be hotter over here and colder over here because heat transfer moves from hot to cold, right? So even if T1 and T2 were not given, in terms of like which thermocouple is which, I should just be able to give you these temperatures and you should be able to figure out which direction the heat is going and therefore which one of these is reading hotter than the other one. So that might be something that I throw at you on like a quiz or something like that, just to make sure you're paying attention. Okay. The other thing to note here is remember this. We have multimodal heat transfer, right? So we're going to use a surface energy balance. If I can get back to it, surface energy balance, right? So here's my surface. It's got convection on one side, it's got conduction on the other side. We're going to set those two heat transfer terms equal to each other, and do the calculation from there. Okay, the book told me that I can, I think the book told me, oh, no, no. Okay. It didn't give me any assumptions. Okay. So I'm going to make some engineering assumptions, which you guys, I think, are skilled at this from your other classes. So I won't, delve into this too deeply, but here are the assumptions. So first, we're in steady state. Second, we have one-dimensional conduction in the casting. And third, we have constant material properties, so constant K. The approach that I'm going to take is I'm going to perform an energy balance on the control volume, just like I described before, encompassing the heating surface. I'm going to set convection equal to conduction, and then I'm going to solve for the things that I don't know, which you'll find are just the convection coefficient. Okay, so here's me doing that. So I've got my energy balance, right? So here's the energy balance. This is my control volume. I've got a control surface just upstream and a surface just downstream, or a control surface just downstream of where this multimodal heat transfer occurs. And I've drawn this again kind of with exaggerated thickness, but it is not thick enough to encompass any mass. It's just right there at the surface, no mass. So it cannot support any mass, or sorry, cannot support any energy, holding on to energy. Trying to think of the term for that, having a senior moment. So it can't hold energy. Um, and we're in steady state, right? So if I do a first law energy balance on this control volume, the time derivative of energy with respect to time, this is a closed system, right? There's no mass that's entering or leaving the system because there's no mass in the system at all to begin with. So the change in energy of a closed system is just the change of internal energy of the closed system with respect to time. You should remember that from thermo. And then here's my first law. So Q dot in minus Q dot out plus W dot in minus W dot out, that equals this change of energy. I will make a quick kind of aside here, right? You guys might have seen this as like E equals Q minus W, right? The compact form of the first law of thermodynamics. Please never write that again. It's not wrong. It just lends itself to making mistakes. So whenever I write the first law of thermodynamics, it takes a little more time, but I always write it out in all of its glory, because my favorite thing in the entire world to do is to cross out terms, which I'm doing here, right? And for those of you who took fluids with me, you remember Peter's theorem. I will not delve so deep into Peter's theorem in this class, but it'll be an inside joke between those of us who have taken fluids together. But I always try to explain when I'm crossing out terms why I'm crossing them out. That's basically Peter's theorem. And so I'm crossing out the du dt term because remember I assumed steady state, right? So no time derivatives. And there's no work transfer anywhere in this problem, right? Like there's no shaft work, there's no work. So all the work terms are gone. So I've just got Q in equals Q out is equal to 0. So that's this. Q dot in equals Q dot out is equal to 0. And the only types of heat transfer that I have are conduction and convection. And if you look at the arrows, I've got convection going in, right? So that should be positive. And then I've got conduction going out. So that should be negative, right? That should be this one. And so if I take this guy and I rewrite it where I've got Q in equals Q out, I can identify convection is in, conduction is out or negative, and so you could see how these things fall out. So Q convection is equal to Q conduction. All the negative signs go away because they're basically equal and opposite to each other because one is entering, one is leaving. All right, so we've got this set up now. Q convection equals Q conduction. What do I do next? Um, oh. So remember, this is one of those weird situations where um, the outside temperature, let's go back, the outside temperature is hotter than the surface that I'm exchanging heat with. And so remember all the way back here, right? I originally wrote this guy this way, Ts minus T infinity. Why? Because this surface was hotter than the air that it's transferring heat into, and I want Q to be positive, and so T surface minus T infinity, big minus small gives me positive. Check out what's happening here. I have very high temperature, and then here I've got a lower temperature, and so I need to reverse. Oh, oh, there we go. I need to reverse the order of these two to make sure that the heat is going the right way. Right, so hotter temperature first means T infinity minus T surface. Okay, so that's my convective equation, and then my conductive equation is, yeah, we've seen this before, right? K minus T1 over, K times T1 minus T2 over L. Okay, um, I have a problem, which is I would love to be able to solve this for H, which is where I'm going, except I don't know TS, right? I know T infinity, T1, T2, everything else, but I don't know TS. So I have to be creative and figure out a way to get to TS. And it turns out that from my knowledge of conduction, I can figure out what TS is. So TS is not given in the problem statement, but enough information is provided that we can calculate it. Um, so, um, how do I calculate it? Well, I know that I've got one-dimensional heat transfer from the inside surface of this cast metal object all the way from T surface to T1 to T2. And so just like with flow of current in an electrical circuit, if the heat traverses from TS to T1, the same heat must traverse from T1 to T2. And so I can set those two heat transfer rates equal to each other, right? So that's me doing that here. So Q conduction from the surface to 1 is equal to Q double prime conduction from 1 to 2. I know those equations, right? It's just this equation all over again, except S to 1 and then 1 to 2. So here I am doing that. Um, the K is the same in both cases because it's conduction through the same material. So you'll see on my next slide, I'm canceling out those K values because they're the same. Um, it just so happens that the distance from the surface to the first thermocouple is 15 millimeters, and 30 minus 15, the distance from the first thermocouple to the second thermocouple is also 15 millimeters. So those two guys will cancel each other. Not always true, right? I could have set up this problem in such a way where T1 was moved, say 5 millimeters this way, in which case these two would not cancel, but it just worked out in this case that they did. Um, if they didn't cancel, it's fine. You could solve the problem anyway. You know what the values are, but yeah, they canceled, so that's nice. So we're left with T surface minus T1, which is the numerator here, is equal to T1 minus T2, which is the numerator here. I'm just going to solve this guy for TS. Here I am solving for TS. Here I am plugging in the given numbers, and it turns out that T surface is 343 Kelvin, right? So that's how I get T surface. Once I know T surface, I can go back to my equivalency between convection and conduction, set those equal to each other as I did before, and solve for the one thing that I don't know is H, right? That's what I'm going for. So I'm going to take T infinity minus TS. I'm going to move it to the other side of the equation. And now I just plug in numbers, right? I know all these things. Uh-oh. What did I do here? Oh, whoops. Okay, I'll fix this when I post the slides in permanent form. I messed up. I left an area, right? So I solved all these. This is actually good for you guys to see because I mess up all the time too. And perfection is impossible for humans. Um, so this double prime means that I'm doing thermal power per unit area. And we're told that this thing is thick. We're not told exactly what the area is, but we're told that it's thick, which is makes it thick enough to support one-dimensional heat transfer through conduction. And then I get all the way to the end, and all of a sudden this weird 3 meters squared shows up, right? That was I copy and pasted this from that previous problem with the glass pane, and I left this in there by accident. So neglect it. This shouldn't be there. Right, there's no A here, so there shouldn't be a 3 here. So sorry about that. Um, Okay. We know the K value that's given. We know T1, we know T2, those are given. We know the distance from L1 to L2 is 15 millimeters, right? 30 millimeters minus 15 millimeters, 50 millimeters. And we know T infinity, and we now know TS because we solved for it. And so when I plug in the values, I get a nice 333.3 watts per meter squared Kelvin is my H value. Again, neglecting this three, that should not be in there. Okay, I got a green check for getting that right. I've checked this against the solutions in the book, and it is correct. So hopefully you got it too. All right. Third mode of heat transfer is radiation. And let me immediately say that we are not talking about alpha particles, beta particles, gamma emissions. This is not the kind of radiation that kills you. Radiation is kind of a catch-all phrase for transmission of energetic particles across space. In our case, these energetic particles are photons, right? You might get a sunburn, but you're definitely not going to die of, alpha alpha particle emission radiation. Um, so not that kind of radiation, but same phenomena. Um, okay, that's what this is. Just to remind me to tell you that this is not nuclear decay. Okay, so radiation is governed by the Stefan Boltzmann law. So we've got Joseph Stefan, lived from 1835 to 1893. He was the one who kind of empirically was able to derive this from like observation. And then one of my favorite human beings in the whole world, Ludwig Boltzmann. I named my cat Boltzmann. I love this guy. 1844 to 1906. Boltzmann actually figured out the underlying quantum mechanics to solve this from first principles. So both of their names are attached to it. Stefan figured out what the equation was, and then Boltzmann proved that it was right. So radiation energy is emitted by all hot surfaces. Any surface that's above 0 Kelvin, right, has some thermal energy associated with it, and it will emit energy, which is called emissive power, E. The Stefan Boltzmann law prescribes an upper limit to emissive power. Here it is. So E, emissive power, is equal to the surface emissivity times the emissive power for a black body, which I'll explain in a second. And it turns out that this E sub B can be represented as Stefan Boltzmann constant times the surface temperature to the fourth power. I'll describe what this is in a second on the next slide. Um, so surface emissivity is a value from 0 to 1. It can't be less than 0, can't be greater than 1. And that is, it basically tells you how much of the energy that is contained within an object gets emitted at the surface. Right. So a perfect emitter is something called a black body. We'll talk when we get into radiation about why that is. But imagine it's something that's painted like perfectly black. It sounds really weird because you think of black as like the perfect absorber. Turns out that good absorbers are also good emitters. And so a good emitter of radiation also in an idealized situation would appear black. So EB is the emissive power of a perfect emitter, also called a black body. And then TS, this is the surface temperature. So this is a more practical, like measurable property, which is temperature of the surface. Okay. So as said already, all surfaces radiate energy. So radiation is incident on all surfaces from their surroundings, right? This to me is like fascinating, right? So um, we are emitting energy to the room that we're in, but at the same time, the walls of the room that we're in are emitting energy to us. And that is true of every object in the room, right? They're all emitting energy at us. We're emitting energy at them. And there's sort of this massive, like dance, if you will, this ballet of energy transmission between objects at different temperatures in enclosed spaces. It's actually amazing when you think about it. Um, so the rate of all incoming radiation um, is incident on a unit area of a surface, or I should say, incident on a unit area of a surface is called irradiation. Irradiation, which is called G, is the variable used for irradiation. So as I'm sitting here and all of the spaces around me are all like, blasting me with thermal radiation, the irradiation that I'm experiencing is capital G. Um, Irradiation may be absorbed. If it's absorbed, then it increases the internal energy of the material. And so irradiation energy absorption rate per unit surface area is governed by a term called absorptivity. Just like emissivity, absorptivity is a number between 0 and 1, can't be less than 0, can't be bigger than 1. And this is a material property that you look up, just like emissivity. It's something that you look up. It's usually a function of temperature. So the absolute irradiation, so this is like everything that's hitting you, all the energy that's hitting you from your surroundings, um, is equal to the absorptivity times uh, ooh, no, I'm sorry. I'm sorry. ABS is for absorbed. Absorbed. Like absolute. No, 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 no. This is absorbed. G absorbed. Sorry, messed that up. This is the energy that you absorb. Is equal to your absorptivity, right, times the total amount of energy that gets irradiated onto you. Right. Okay, that makes sense. So energy that you absorb is equal to your absorptivity times total irradiated energy. Okay, makes sense. All right. Typically, when we solve heat transfer problems, unless you're like a satellite out in space and you're not in thermal communication with anything, typically your objects are enclosed, surrounded by something. Oftentimes, it's a room. It could even be just the sky, the ambient environment. And more often than not, the temperature of the surroundings does not equal the temperature of the surface. And so the um, irradiation that your surface is experiencing is this Stefan Boltzmann constant, which we saw before, but I didn't describe, times the surface temperature, surrounding temperature, right? Surrounding temperature, T, sir, too many S's. Surrounding temperature raised to the fourth power. This little guy here, this is a sigma, but in Greek, and that is the Stefan Boltzmann constant. It is a constant value, 5.67 times 10 to the minus eighth watts per meter squared Kelvin to the fourth. Notice the fourth power here, the fourth power here, those cancel out, and you end up with irradiation being in units of watts per meter squared, right? Just like all of the other energy flux terms that we talked about. So if you put all these pieces together, right? So I'm now imagining I have a surface, and the surface is both emitting radiation energy and it's also absorbing radiation energy from a surrounding environment. The object itself has a higher temperature than the surroundings. And by the way, a higher temperature than any air that might be in here, right? Air is opaque to this. Um, this is the equation that I could write for the total radiation energy flux. So it's going to be the amount of energy that my object is emitting, right? So emissivity times its idealized black body emissivity. Or sorry, it's black body. Let me get the term right. Emissive power. There we go. Yep, emissive power. And then minus the amount of energy that it's absorbing, right? So alpha times irradiation. Okay, these two things are really abstract, right? Like, like hard to measure irradiation, hard to measure um, the emissive power. Sorry, I keep getting the word wrong. Emissive power. And so we want to convert this into something measurable like a temperature. Well, hey, we can do that because we got this equation for emissivity. And on the previous slide, we have this equation for emissive power, both in terms of temperature. So I'm going to just take those equations that are emissive power and G in terms of temperature, and I'm going to just plug them in, and out pops this. Although something weird happened between this equation and this equation, which is my absorptivity went away. Where did it go? Well, we make an engineering assumption, which is actually true a lot of the time, called the Gray assumption. And in the Gray assumption, we are assuming that the emissivity and the absorptivity of a surface are the same. Remember, I mentioned when we talked about black body emitters that a good emitter is a good absorber of energy. Turns out that it's a pretty good engineering assumption if you have an emitter to assume that its absorption is the same as its emission or as emissivity. Not always true, but reasonably good first assumption to just set those two equal to each other. So if those two are equal to each other, then um, absorptivity and emissivity are the same. That comes out of the equation as the emissivity, and you end up with this expression for radiative heat transfer in terms of emissivity, which you can look up, Stefan Boltzmann, which is a constant, one surface to the fourth power, surface temperature to the fourth power, and then your surroundings temperature raised to the fourth power. So that's our radiation equation. All right, let's do an example. And as mentioned, right, multimodal heat transfer is the reality of our our earthbound situation here, right? We always have air around us unless we're in a very unusual situation where we're somehow submerged or in a vacuum chamber. And so usually when you solve real world problems that involve radiation, they also involve convection and sometimes even conduction. So this is one of those multimodal problems, which is again why we're doing the energy balance on the surface, right? Because we're going to equate all these things together. All right, so we have a galvanized steel sheet. We're given its emissivity is 0.13. And again, emissivity is a function of temperature. So we're going to just assume for now that it's fixed. But when you solve these problems out in the real world, sometimes they're iterative, right? So you make an assumption about what emissivity is, and then you solve for the temperature, and you realize, oh darn, the temperature is actually much, much higher than I originally imagined. And so I have to go back and use a different emissivity that's associated with the new temperature. And then you have to solve the problem all over again to come up with the new temperature, check the emissivity and so forth. So it sometimes does tend to be iterative. Um, but you guys are very good at programming, and I'm sure you can write software that would, or you could just use AI that would solve that iteration problem for you. Back in my day, we had to do it all by hand. So anyway, we will hope that the end result that we get for the temperature of this surface is around 300 Kelvin, and this emissivity is correct. Okay, so we have this emissivity, and we know that its solar irradiation absorptivity is 0.65, right? So this is one of those situations where emissivity and absorptivity are not the same. This is not a gray body, not the gray assumption. Those two numbers are different. But if they weren't, the first thing that I would do is say, yes, absorptivity is also 0.13, right? But here the numbers are given, so don't need to do that. Okay, so we're asked to determine the surface temperature of galvanized steel a galvanized steel roof on a day when the radiation from the sun is 750 watts per meter squared, right? Now, this is like a winter day in Florida, right? So it's usually 1,000 watts per meter squared is kind of the standard number for our part of the world. So 750 watts per meter squared. The ambient temperature is just under 300 Kelvin, so 298. 0.15 Kelvin, and we're given a convective heat transfer coefficient of 7 watts per meter squared. Yeah, okay, 7 watts. I'm looking at that. I'm like, wait a minute, shouldn't there be, yeah, watts per meter squared. Okay, so, oh, no, watts per meter squared Kelvin. Ha, okay, that's what I was looking for. I didn't see this Kelvin in there. Watts per meter squared Kelvin. Okay, like there should definitely be a Kelvin. Where did it go? There it is. All right. Um, We're also told to assume that the bottom surface of the steel is insulated. So we're not losing any heat out the bottom, right? So you can imagine this is a roof. It's really well insulated to keep the cold inside. So that's where this assumption is coming from. Okay. So we're going to make a couple of additional engineering assumptions. Steady state is a good one. Environment being treated as large surroundings at a temperature of 298.15 Kelvin. what I didn't say here, which I should, I'll add this when I finish the slide deck, is that, um, what was I about to say? Sorry, I lost my train of thought. That properties are constant. Properties are constant, right? So um, no spatial or time changes in things like convection, heat transfer coefficients, or E or A. And then, oh, look at this. Roof surface is gray. Okay, I've outsmarted myself here. So what I just said before was that the emissivity and the absorptivity are not the same value because the absorptivity is given. But look at this. Solar irradiation absorptivity is this value. So we're given the absorptivity of the steel for a very, very specific emitter, which is the sun. um, in all other cases, right, when we're interacting with the surrounding environment, we should assume that this is gray, right? So we should use that absorptivity equals emissivity equals 0.13. Oh, that's so interesting. Okay, this is a very cool problem. I didn't actually realize that as I selected this. Okay, it's okay. It's okay. We'll get it. We'll get it solved anyway. Okay. So that's why I say here roof surface is gray, right? If you do need to calculate the radiation between the environment and the surface, you'd end up using that emissivity equals absorptivity. But in calculating the energy transmission between the sun, which is way out here somewhere, and the surface, we're going to use an absorptivity of 0.65. Okay, that's very cool. All right. Same approach as we've used before. We're going to perform an energy control surface, perform a control surface energy balance on the steel roof, and we're going to do it on a per unit area basis. So here is my control volume, same as before. It's very, very thin, so I don't have any mass in there, but it does experience all of the energy fluxes, and I'm going to use it to account for all of the energy fluxes, do my first law energy balance, and then be able to set all those energy fluxes equal to each other, and then um, swap in my temperature equations for my energy equations, and then solve for temperature. So same approach we've done before. This one's just, it's radiation. Okay, so I've got my system, the change in energy of my system with respect to time. This is a closed system. I don't have any flux of mass entering or leaving because there's no mass in the system. And so the the energy is the internal energy. But since we're at steady state, the internal energy is zero. I definitely have heat transfer in, and I definitely have heat transfer out. So those two terms stay. I do not have any work transfer. There's no shaft work. There's no change in volume, pressure work, nothing like that. So these two terms are gone. And I'm left with the same thing that I got before, which is Q in minus Q out is equal to, I should say Q dot in minus Q dot out, right? These are energy fluxes, are equal to 0. And then I just need to figure out what these things are, right? So, and where the plus signs and the minus signs are. So if I look at the problem drawing, here is the irradiation coming in from the sun, G irradiation sub sun, 750 watts per meter squared. So that's definitely incoming. That's going to be positive. I have radiation. So this is the steel sheet radiating to the surroundings. That is energy flux that is leaving. So that's going to be negative, right? Negative. And then I have convection, right? So this sun is going to heat this thing up. It's going to get hot and it's going to start convecting to the surroundings as well. And I'm given all the parameters to calculate the convective heat transfer coefficient. So because energy is leaving through convection, this value is also negative, right? So when I sum them up in this way, right, this is plus, this is minus, they're equal to 0 because there's no stored energy in the system. Okay, steady state. All right. So here's just that same line written all over again so you can see it. And then here is me plugging into this equation the temperature dependent terms that I know. So the irradiation is the irradiation coming in from the sun times the absorptivity of the steel with respect to the sun. That value was given, right? 0.65, right? And then here is my radiation temperature equation. And then here's my convective temperature equation. And notice here, I've got Ts minus T surface. Why? Because Ts is hot, right? The surface of this metal roof is hot relative to the environment. So this term comes first, the environment comes second to make sure that this is positive, and then that negative sign comes from the fact that it's energy leaving, right? So that's just got to make sure that we arrange those correctly. Don't want this to inadvertently be T surface minus Ts and have this term be flipped in the wrong direction. Okay, so I know this first term, right? It's 0.65 times 750 watts per meter squared. So that term is 487.5 watts per meter squared. Notice absorptivity is unitless, no units, right? So, but I'm solving this on a thermal power per unit area basis, so that works out fine. I've got a problem now, right? Which is I'm looking for TS. That's what I'm trying to solve for. I have TS to the fourth power here. I have TS raised to no power here. Everything else in the equation I know, right? Emissivity is given. Absorptivity, turns out I didn't need that. Um, Stefan Boltzmann is a constant. H is given, but T to the fourth and T. So this is a situation where you're going to have to use some sort of solver. So that's what I did. I put the remaining equation into a solver. So I had a T fourth term in there and I had a T term in there. And the solver was able to give me the real solution, which is 350 Kelvin for TS for that surface. And I checked with the solution in the book, and okay, yes, it's 350 Kelvin. So I did it right. Good for me. Green check. Okay. Just sort of as like a sanity check, I went in back now that I know what the surface temperature is. So two sanity checks. So one, right? Remember all the way back here, we had emissivity of 0.13 around 300 Kelvin. And so is 350 close enough to 300 Kelvin that this emissivity value doesn't change? For this problem, yes, but you probably want to go back and check. 50 degrees Kelvin is a big temperature jump. So the emissivity might have changed enough that you need to go back in and recalculate, right? And it would show up right here in your calculation. I didn't do it, but you could if you wanted to be really, really, really precise with your value. So that value is there. This value is known. T surface is known. T surroundings is known. I plugged all those in. And this is the amount of energy, 59 watts per meter squared, that's getting radiated away from the steel roof to the environment, not to the sun, to the environment, because the environment is colder than the roof, right? So about 60 watts per square meter. This H is my heat transfer coefficient, convection coefficient that I know. I know T surface, I know T surroundings. Calculated 428 watts per meter squared. This is the convective heat transfer coefficient, right? Again, the roof is hotter than the surroundings, so this is going to be heat transfer away. We actually have three different heat transfer modes here. Well, I should say two and a half different heat transfer modes here. So we have convection, about 430 watts per meter squared. We have radiation leaving, about 60 watts per meter squared, and then we have irradiation coming in from the sun, about 490 watts per meter squared. So pretty interesting multimodal heat transfer problem. Okay. Hopefully this was interesting and fun. I had a lot of fun like solving these problems for you and describing all this stuff. As I said, I love this stuff. This like energy, thermal fluids, thermodynamics, fluids, heat transfer. This is my area. And I very rarely get to teach these classes. So really, really happy to have the chance to teach you guys this. And sorry again that it started out as such a dumpster fire, but it will definitely get better. Okay, so that's the last slide. If you need any, have any questions, feel free to send me a message on Teams or email me. I am going to, you guys are watching this now. I should have said this at the beginning. I'm going to drop this into perusal and have you guys comment on it. So I'm happy to read all your comments. And if you have questions that you just want to drop into perusal, I will try to read those and answer them as well. Okay. Really appreciate your time and attention. And of course, your patience and your grace with me getting the class spooled up. That's the end of this presentation. Thank you for your time and attention, and I will see you in the next one.